Hello, everybody. My name is Thomas Adler-Mandile. I'm from Fitchburg State University, and I've been working on the synthesis and characterization of insect pheromones with Dr. Mathangi Krishnamurthy. We've been making blattellaquinone and its analogues. This is the structure of blattellaquinone here on the left, and what the material looks like as a bulk material on the right. It's the sex pheromone of the German cockroach. Um, and you can see it's got a quinone moiety here, which is pretty interesting as far as the structure of pheromones goes. And it's also got an ester group. That's what we'll be varying to make the analogues. We changed the side chain of the ester group to make different analogues. So the isobutyl side chain is the natural product. And then we also made analogs with the methyl side chain, a propyl side chain, and a phenyl side chain. So the analog structure here, R1 represents any of these. In order to make the analogs, it was two steps. We started with 2,5-dimethoxybenzyl alcohol, and we esterified it using an acid chloride and pyridine. And then what we did is we oxidized that right to the quinone with ceric ammonium nitrate in acetonitrile water. The compounds that we produced were purified with column chromatography. You can see one of the columns here on the right. The yellow material in the lower band is the product, and these orange and red bands are the side products. And once we had made the analogs, we analyzed them using proton NMR and IR spectroscopy to confirm their structure. We then tested the activity of blattellaquinone in Madagascar hissing cockroaches. So they're a different species than what the pheromone was originally found in. So, we weren't sure if it would do anything, and it turned out that they didn't really have a significant response to these type of pheromones. We tested them at a variety of concentrations to make sure. And we did this by soaking solutions of the pheromones in DCM, soaking pieces of paper in that, and letting them dry, and then testing that against paper just soaked in plain DCM and left to dry, and see which strip of paper that they go towards, and they seem to exhibit no preference. So we decided to just move on to optimizing the synthesis, which was really the main point of this project anyway. So you can see what yields we got using the original procedure, the ceric ammonium nitrate and the acetonitrile water. Reaction 1 is pretty consistently good yielding, except for a couple here where there was some issue with purification, but you can get yields of above 90% with that first reaction, so that wasn't really a problem. But you can see here the oxidation step, right? The ceric ammonium nitrate step is pretty consistently inefficient. So we are focusing on optimizing the oxidation procedure. So yeah, so the best yield you could get with the ceric ammonium nitrate is about 38%. But we switched the solvent to DMSO instead of acetonitrile, and that increased the yield to about 45%, right? So there's a bit of an improvement there. The main side reactions that make it inefficient are dimerization of the quinone products and ester hydrolysis, because there's an ester group. There's an ester group here, and if that gets hydrolyzed, then this alcohol here can get oxidized, and that leads to breakdown. The dimerization occurs at these carbons on the side of the quinone here. So yeah, when these carbons are exposed, that can lead to the dimerization. But yeah, the DMSO procedure worked a little bit better. And we're focusing on improving this even more, right? Because even with the DMSO procedure, you get new side products that you didn't get with the other procedure that can be difficult to separate. And ester hydrolysis might still be a problem because the ceric ammonium nitrate oxidation produces acid, which can hydrolyze the ester. So at the end of the reaction, you end up with a pretty acidic solution. So the idea was we could use silver oxide instead of ceric ammonium nitrate, which doesn't produce acid when it oxidizes the material. So we can see how that goes. It's typically a pretty clean oxidant, so we might get fewer side products with that. But we have yet to test that out. So that's what we've done so far, and where we're planning on going with it. And yeah, that's about it. So thank you guys so much for listening, and I'll see you at the conference.